Hi. In this video, I'm going to go over our physics journal about force diagrams. So the question that's going to be guiding our question or our notes today is how can we represent an object, or how can we represent all the forces on an object? A force diagram, so the big idea is that a force diagram, or sometimes we call this a free body diagram, so you'll see me use either force diagram or free body diagram interchangeably. A force diagram uses vectors to represent, meaning basically arrows with links that matter, to represent the forces on an object. So let's imagine that we have a crate is pushed at a constant speed. Here's a little picture of a person pushing a crate. The rules for the diagram are as follows. So the first thing you want to identify what you are drawing the diagram for. So in this case, are we drawing it for the crate, or are we drawing it for the person, or are we drawing it for the ground? Probably it would make most, we're going to be drawing it for the crate. It's usually like the inanimate object in the diagram, generally speaking. Less common for it to be the person, though not unheard of. Draw the object as a dot. So we don't want to redraw a crate every time. We want our diagram to be really simple so that it's easy to just see what the forces are. And so if you make your object kind of a complicated drawing, one that takes time, and then two, it actually detracts from like your arrows, right? It makes it harder to read the diagram. Always draw the force vectors coming out of the dot, never into the dot. So you might, like if someone was like pushing down on something, you might want to draw the arrow like into into it. Like this person is pushing to the right, but they're pushing it. So you might want to draw like the arrow going into the dot, but you don't want to do that. Any pushes that are to the right want to come out to the dot, pointing to the right. Any pushes to the left, you want to come out to the left. Only include forces acting on the object, not by the object. So this one gets a little bit tricky to explain without having specific examples, but like in the case of this one up here, the crate is like pushing on the person to the left, and so we wouldn't include that because it's a force by the crate, not on the crate. That's not a really great example, I apologize, but I think it'll make a little bit more sense as we go along. That will start to make sense. But label the force vectors with F and then subscript what is causing it. So here are common forces down here. We have Fg for gravity, Fn for normal force, Ff for friction, and Ft for tension. Those are your common four. If you have something that doesn't fit one of those, you could label it as like F push. If it was, for example, from the person, or pull. Wrote pull, that's weird. I should probably have written push. So, but anyway, that's kind of how the common ones in the subscript thing. So you can have vector or ones other than these ones. You just would have to label it something else. Um, for example, push should have been push. Sorry. The length of the vectors represent the magnitude of the force. So if it's a bigger, so in this case, right, let's note that these two are the same length because they should be the same size, because we should have balanced forces. However, right, if I made one bigger, that would mean I would have like a net force to the right. So the length of the vectors is important relative to the other vectors. So same thing vertically, we can see that we have the normal force is equal to the gravity, giving us balanced forces vertically, so we don't accelerate vertically. So let's actually just take a quick moment. This force diagram right here is representing this situation up here. So the guy, or you, I guess, are pushing it to the right, so hence the push force. It's at a constant speed, meaning that you're going to have balanced forces. The net force will be zero because you're not accelerating. So when we go down here to look at this, your pull force and your friction force are equal. And so they're canceling each other out, basically, meaning that your net force is zero. So you're going to move at a constant, the crate will move at a constant speed. We have the force of gravity, which is pulling down on this object on the crate. We have the normal force, which is pushing up on that crate. The normal force is a force exerted by a surface. I have that's, we'll look at that in just a second. I have definitions for you. Um, but that's the upward force exerted by the surface. It has to be perpendicular to your surface. So more on that in a second. Um, Often you want to think about this as what things are touching the object, right? So there's two things touching this crate. The first one is the ground, and the second one is you. And so basically, there's only one force that can be exerted without touching something, and that is gravity. So that explains the gravity for one. You are touching it, so that explains the push force here. And then a surface, the ground, can only apply two different forces. It can either apply a normal force, which is perpendicular to it, or it can apply a friction force, which is parallel to it. So those are the only two. So generally, the way to approach these diagrams is to just think about like what is touching it, and then what forces would be applied by what is touching it. So good way to think about it. Moving along, next up are some definitions, right? So we have the normal force, which is a force exerted by the surface perpendicular to that surface. So in this case, it is the surface of the table or the ground pushing up on the crate. That surface can only push perpendicular to it, which would be straight up. Um, a tension force is a force exerted by a rope, cable, or string, just, some sort of cord of some sort, or, would be a tension, right? So you could like talk about the tension in the rope or something like that. That's the force in that rope as you pull it along. Lastly, we have friction force here. It's a resistance force always parallel to the surface and opposing the motion. You pull it to the right, friction goes to the left. So on, it's a resistance force, so it can never be the force that causes something to move. So it can't be bigger than whatever the pull force is or something like that. It can't like make something accelerate. All right, with that, let's go ahead and look at some example problems. So it says, right, draw the diagrams for the following situations. So let's take a look at those. So in this case, we have a bowling ball rolls through the no touch zone. So the no touch zone is a spot that like when we do the obstacle course with the bowling ball in class, there's like 4 cones, and as the ball goes through the 4 cones, you can't touch it. So there's no forces being applied to that, like by the broom. So let's see here. So first up, if we think about what is touching it, the only thing that is touching this ball is the ground. So therefore, we could have, well, obviously we're gonna have gravity. So let's go ahead and put gravity in there. Gravity is going to point straight down, Ft, and it's touching a surface, right? It's touching the ground. The ground could apply two different forces. It can apply the normal force, and it can apply the force of friction. So obviously it's going to have a normal force. The normal force is going to be opposite to the force of gravity, and it's going to be the same length because it's basically just supporting the object, right? Gravity's applying a downward force, the table is applying an upward force equal to that of gravity. In this case, the bowling ball has very little friction on it. So we would say we're not going to have a friction force because remember, surfaces could also apply a friction force. There's going to be no friction force on this one just because to a ball that rolls along, the force of friction is basically zero. If we did have a force of friction, it would be to the right. The other way we know we're not going to have a force of friction is since we can't have a push force because there's no because right, it's a no touch zone, so you can't touch it with the broom. Since there can't be a push force to the left, there can't be a friction force to the right because we do need to have balance forces horizontally because the thing has to move at a constant speed. It doesn't specifically say this here, but again, in the actual lab, the ball moves at a constant speed through the no touch zone. So there we go. That's it. I hold bag of slugs. It's a weird thing to hold. There's only two things touching the bag, or one thing touching the bag, right? That's me. So we of course have gravity still acting on the slugs. So gravity is pulling this bag downwards. I am pulling the bag upwards. So let's call it F hand maybe. All right, and then this last one is probably the most interesting one and useful one. So we have a cart. So I push a cart and it speeds up. So if we think about there's two things touching the cart. There is the ground and there is me. So that's two different things. So first up, let's just think about we got our force of gravity. All right, let's start with that. Start with the easy things. So now let's tackle like I am pushing it, right? So let's do that. The ground is touching it, and so the ground can apply two different forces, right? So then the ground can apply a normal force, so that's going to be there to cancel out this force of gravity. And there's also going to be um, right. So you could. It doesn't say anything about friction, so we right whether this cart is frictionless or not, we don't really know. If you would like to, so on the starter thing or like looking at this, we could stop here if we wanted to, right? I push a cart and it speeds up, right? It speeds up, meaning that there must be a net force to the left because there's an acceleration, so therefore it must go faster, right? So I need a net force to the left. So I have a net force, I could be done. If you did want to say, oh, there's probably some friction, the friction does need to be less than the push force so that there's a net force so that it speeds up. So if I wanted to say that there's some friction, which is fine, we can assume that there's friction if you'd like, but we do need to make sure that it's smaller than the push force because if it's accelerating, right? If it's speeding up, then I need a net force, meaning a bigger force to the left than I have to the right. So there we go. Those are our notes for today. Thanks for watching. Bye.